Hello and welcome. In this video we are going to take a look at a graph theory algorithm called the breadth first search. And this is going to involve finding the shortest distance between a vertex and every other vertex in a graph. There are two possible ways this type of thinking might evolve. The first involves an unweighted graph where each edge is worth the same as every other edge. So for example, this graph down here, we do not have any labels on the edges. These are perhaps the physical distance is not itself important. And these could just be networks of friends, for example. And we may want to know the shortest path between each vertex and every other vertex in the graph. So the second involves a weighted graph where each value has a different, or each edge has a different value, which could represent cost, profit, physical distance, or some other metric. So as an example here, these could be, again, friends in a network. These could be diseases in a network. And it might make sense to ask, what is the shortest distance from L to every other vertex in the graph? And because we have, looks like we have two ends here, let's distinguish these. Let's call this one M down here. We'll call this vertex M to make this a little more convenient. So maybe we want to know if L is a disease, what's the shortest way in which L is linked to disease E, for instance. So we could kind of just begin sketching this out and say, well, from L to A, that's the shortest distance to A. L to N directly, that's the shortest distance to N. L to I, that's the shortest distance from L to I. To get to Y, for instance, it looks like we could go from L to N to Y, and so we could make it there in a path of length 2. There is an algorithm that tells us how to do this, and it follows the same sort of logic. We're going to reach, as opposed to follow any path all the way downstream, what we're going to do is we're going to take a look at all the vertices that are adjacent to our first vertex. So A, N, and I. And obviously that would mean that the shortest distance from L to A is going to be directly from L to A. From L to N, from L to I, shortest paths are direct distances. Of course, we don't want to look at this as L to A to N, because clearly you could make it to N in a path of length 1 as opposed to a path of length 2. So the idea here is that we look at all the nearest neighbors, and the nearest neighbors are, those distances are already optimized immediately. From there, once we look at all the neighbors of L, we look at all the neighbors of L. So for instance, to get to Y, now if I look at all the neighbors of N, I see that Y is the closest neighbor to N, and then I could say L to N to Y is the shortest distance to get from L to Y. So this algorithm requires having some starting vertex. From there, we visit each vertex in a special sequence and denote the least number of steps required to get from that vertex to each other vertex. So here's how this algorithm works, and we're going to be exploring some pseudocode, which sort of just gives us the logic of what to do. So step 1, we're going to label S, which is our starting vertex, assign S the label 0, and let S have no predecessor. Assign S to this list that we're going to be creating, or perhaps this set, L, that's going to keep track of all the vertices that we've been to. So assign S the label 0 and let S have no predecessors. So the way we're going to do that is, in this case, our starting vertex is the vertex L, and we're going to say we're going to set K equal to 0. So down here, our list L, which I'll kind of draw as a squiggly L, is going to equal the set consisting of our starting vertex, which is vertex L. Right now, we've set K equal to 0. This is just going to keep track of distances, so K is the current distance. And now we're going to go through this repeat process until we've visited every single vertex in the graph. So the first step is to replace k with k plus 1. Oh, and again, assign s the label 0 and let s have no predecessor. So the way we're going to indicate that is down here we're going to say the shortest distance from L to L is a distance of 0, that's where our label 0 comes from, and let s have no predecessor. So in parentheses, I'm just going to put a little dash in there to say that L is 0 units away from itself and it doesn't have any predecessor, meaning we didn't arrive at L from any other vertex. Next, replace k with k plus 1. So k will no longer be 0. K will now be equal to 1. And now we're going to continue to repeat this process down here. While L contains a vertex with label k minus 1 that is adjacent to a vertex W not in L, assign the label k to W, assign V to be the predecessor of W, include W in the list. So while L contains a vertex V with label k minus 1, so right now k minus 1 is 0, and so far there is a vertex in there with label 0 that is adjacent to a vertex W not in L. So we have to look at all the vertices that L is adjacent to. So it's adjacent to A, to N, to I. The order here is not important. Assign the label K to W. Okay, so our first W, our first next vertex, we'll say is A, and we are going to assign the label K to it, which now is 1, and we're going to list as its predecessor L, because to arrive at A, we've come from vertex L. And now we're going to add that vertex to our list because we've essentially found the shortest distance to it already. Now we're going to repeat this. We're now going to say that distance from L to N is also a W. It's a vertex adjacent to L, and it's going to have a distance of 1 as well. Its predecessor is L, and we are going to add that list, or add that vertex to our list. So that was vertex N. Now we have to keep going. We have to repeat this process while L contains a vertex that is adjacent but is not yet in our list. So these are basically any unlabeled vertices, which includes I. I has a distance of 1. The current value is still k, and the shortest distance there is directly from L. So now that we've completed that process, and now we need to add I to our list. So I is now part of our list, and we've completed this while loop, so we now end the while, and we keep repeating this until no vertex in L is adjacent to a vertex not in L. So basically we're going to keep repeating this process until we've labeled every single vertex. So now we look at all the neighbors of the neighbors. So the most recent label was k equals 1. I'm now going to iterate and replace k with 2 because now I'm going to be looking at vertices that are 2 units away from our starting vertex L. And again, I'm going to look at all the neighbors of all the vertices in L. I've already looked at, I'll kind of just underline L here because we're done with L. Now look at the neighbors of A. Well, the only neighbor of A is N, and N has already been established as a shortest distance. K is currently 2, so I don't want to replace the label on N with 2 coming from A because clearly that's a longer path than going directly to N. So A is done. A doesn't have any neighbors that haven't been labeled already. N does have neighbors that haven't yet been labeled, and that would be just vertex Y and vertex M. So I'm going to look at those guys. So Y is 2 units away from our starting vertex. Its most recent predecessor is N. Same thing for M. It is 2 units away, and the most recent vertex that we came from is N. Next vertex we need to consider, now that we've considered all the neighbors of n, is vertex I. So vertex I is this one here. That one already has a label, so it does not make sense to... Oh, I'm sorry, we need to look at the neighbors of I, which is just m. But m already has a label. It has the shortest distance of 2 coming from n. And you can see here that going L to n to m is the same distance as L to I to m. So there's no need to update that label saying that its distance is 2, most recent predecessor is I. These edge lengths are not significant here. These do not signify some physical distance. A connection is a connection, and they're all worth 1 unit. So in essence, you could label all these edges with a 1, and that would still be consistent with what we're trying to achieve here. So, and we've not added the vertices that we've just visited. So we've just labeled y and m, so those belong in our set here. Y and m. And now we need to look at all the neighbors of y and m. So let's go ahead and update k to be 3, since we've just iterated through this loop. And now we're going to look at the neighbors of y and m. So the neighbors of y, the only neighbor is e. And so since the current value is 3, the current k value, as the most recent predecessor y, I can now label that vertex and add e to the list. And I'm now done with vertex y. Vertex m, its only neighbor is e, but e has already been labeled. Had we visited m before we visited y, then sure, e would have had the label 3, most recent predecessor m. But the exact path of getting from L to every other vertex in the shortest amount of distance is not itself important. The fact that we've optimized that the shortest path to get from L to E is via a walk of length 3, L to N to M to E. L to N to Y to E. But L to N to M to E would have been another path. So if we had visited M first, then we would have labeled this as 3 coming from M. So we're done with M, we're done with E. There are no other vertices to visit. We see that we have now officially, there's no vertex in L that's adjacent to a vertex not in L. All these vertices this is the whole set of vertices in the graph. Step 3 is to construct a shortest path to a vertex. If a vertex T is in L, that is, if you pick a vertex in L, the label on T is its distance from S. So, for instance, the distance to E is 3. And a shortest path from S, our starting vertex, to this arbitrary vertex T is formed by taking in reverse order T, the predecessor of T, the predecessor of the predecessor of T, and so forth until S is reached. Otherwise, there is no path from S to T. So this is an important step because you could have a graph that is not connected, and you could have one lone vertex, and this algorithm would, in essence, never terminate because we would never add that last vertex to the set if we didn't consider the if-then case of if there's not even a way to get to that vertex, then there's not going to be a path. Fortunately, we have a connected graph. It is possible to get to every vertex from any vertex in the graph. And so now, by listing out the paths, for example, if I want to know the distance to vertex E, I just have to backtrack now. So I can make it to vertex E in a distance of 3. And the most recent predecessor of E is Y. And the most recent predecessor of Y is N. And the most recent predecessor of N is L. And you can see that this is now a path of length 3. L to N, N to Y, Y to E. And we can do the same thing for every other vertex. The shortest distance to M, coming from L, well, let's backtrack. The most recent neighbor was N. N's most recent neighbor is L. And so L to N to M, that's our distance of 2. And you can once again see here that that's a walk of length 2. We'll take a look at one more example here. Here is another graph, and we'll look for the shortest path from A to every other vertex. So the first thing we do is, once again, we form our list of vertices that we're keeping track of. Look at all the neighbors of A. So B, E, and D. So right now, K is set equal to 1. And we label, well, K was set equal to 0 to start, and that is only to label our first vertex, which is always labeled as 0 and a dash because it's 0 units away from itself and it has no predecessor. And this is in computer code how you could keep track of what the starting vertex is. So B, its distance is, now if we set K equal to 1, now that we've labeled the starting vertex, B is 1 unit away from A. E is 1 unit away from A. D is 1 unit away from A. And we're going to add those vertices to the set. Again, the order does not matter because this is a set. We're just keeping track of shortest distances, and it doesn't matter what order we visit those vertices in. So we're done with A. We can now set K to be 2. We're now done visiting those neighbors. Now we're going to visit the neighbors of the neighbors. So let's look at vertex B. B has only one neighbor, that is C. So now that K is 2, C's distance is 2. Most recent predecessor is B. We can add C to the set. And we're done with vertex B. We now look at vertex E. Its neighbors are C and F. C has already been labeled with the shortest distance. So yeah, another path would be A to E to C. We've already labeled A to B to C as a possible shortest path. And so the only other neighbor E has is F. So F will have a distance of 2, most recent predecessor E. So we'll add F to this set. We're done with vertex E. We now look at the neighbors of D, but D does not have any other neighbors that haven't been labeled yet. D has a neighbor of E, but you can see that there's already a shorter path established. Vertex C doesn't have any other neighbors. I mean, it has E and F, but clearly to go from C to E, that's A, B, C, E. That's a long path. A to E is already a shortest distance. Same thing from A to B to C to F. That would require a walk of length 3. So basically, now that you see every vertex is labeled, there are no other vertices to visit. We're not going to update the value of K. We've now populated the entire list of every vertex in that set. The algorithm terminates, and if we want to find the shortest distance to F, for example, from A, then we already know we can do it in a distance of 2. And the most recent predecessor is E. And then E's recent predecessor is A. So you can see there is our A to E to F is our shortest path to get to F. And that's pretty much the sum of its parts. That is how the breadth first search algorithm works. With more vertices, we would just continue repeating this process.